All right, guys, so it's time. Let's get started. Today we're gonna do some problems on combinatorics and probability. All right, so the first one is a probability question giving you two dice, one red and one green, so which are distinct. Our road found the probability that exactly one of the dice is a 6 and the sum of the dice is at least 10. And the last part is the values of the two dice are different. So I will give you guys 3 or 4 minutes to work on this question and we can talk about it. All right, anyone has an idea on the first part, part A? How are we gonna find the probability that exactly one of the dice is a 6? So there should be multiple ways to solve this part.
Well, first we need the total outcomes, which is 6 squared.
So let me write this. Okay. So you said the total outcomes should be 6 squared, which is also like the sample space. And what are you going to put right here.
There are 6 different outcomes where exactly one of the dice, or there are exactly 5 outcomes where exactly one of the dice is 6.
So yeah, so there's one outcome, so exactly one of the dice is 6. And what about the other one? So the dice are distinct.
Yeah, it's 5 because either the red dice could be 6 or the green dice could be 6. Well, 5 times 2, sorry.
Yep, so it should be 5 times 2. Because for a single 5, you're counting like only for the red or only for a green. So you want to count for the both of them, like when exactly the red dice is 6, and or the exactly green die is a 6. That's where you get the 5 times 2 is 10, which should have 10 over 36, and that simplified would get 5 over 18. And that is your answer for part A. All right, let's look at part B. So this, what is the probability that the sum of the dice is at least 10? If we just write out like all the possible outcomes on each die. And then, so what are the pairs that the sum of dice is at least 10?
4 and 6, 5 and 5, or 6 and 4.
So 4 and 6, is that what you said?
Yeah, 4 and 6, 5 and 5, and 6 and 4.
6 and 4. Okay, so remember that the dice are distinct, so you should also have 6, 6, and 5, 6, and 6 and 5. Is that all? Yep, so that should be all the pairs of sum of dice that is at least 10. Okay, and then that should just be the NV. And then the sample space will just remain the same as 6 squared. And then we have 6 right here because we have six pairs of sum, 6 pairs of the sum of the dice is at least 10. And then that should give you 1, 6. Any questions so far? Okay, now let's look at part C. So the values of the two dice are different. How you want to do this part?
I use the complement rule.
Yep, exactly. We can use the complement rule. So what is exactly the complement part we want to subtract?
So we want to find the complement of the events. So in this case, it would be the value of the dice are the same. And find the probability of that event, and then subtract 1 from that probability.
Yep. So let's use the complementation here. We have n of s minus n of the complement of the events over the sample space. So the complement of the events should just be whatever you get, like the same number for those two dice, which are like 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. So that should give you 6 total pairs, which is 36 minus 6 and over 36. And the result should be 36 over, sorry, should be 30 over 36. And if you simplify that, you will get 5 over 6. And that's your answer for part C.
Would it be correct to also think about it as just a permutation of 6 and 2.
A permutation of 6 and 2.
So just 6 times 5.
Yeah, I think, yeah. Yeah, I think that should also work. Yeah, so for, I guess for this type of questions, there's like multiple ways to solve. So as long as you're, you count for the, as long as like you subtract the overlap or you didn't ignore like any of the edge cases, then it should be fine. Yes, you can use the permutation right here, and then you're still gonna over the sample space, which is 36.
So how would this problem be different if the dice were not distinct?
If it asks like the probability that the values of the two dice.
Yeah, like, so if the problem state was slightly different and it just said 2 dice instead of a red and a green dice.
Oh, you mean like if they're identical?
Yeah, because it makes a point to say that they're distinct, and I want to know if that it influences the problem at all.
Yeah, it does. So if we have like two identical dice, right here, we're not gonna actually count like all of this. Like, so 4, 6, and 6 and 4 should actually be 1. We'll actually only count once. And then as well, like for 5, 6, and 6, 5 should also be counted once. So right here, we should only have, let's see, 1, 2, so 1, 2, 3, and 4 pairs instead of 5, instead of 6.
So the probability would be lower total then. See, that confuses me. Like, changing the color of dice shouldn't change the probability of an outcome.
So I guess it's depending on like how you define the question. If we're thinking about like the sum of the dice is at least 10, there should be let me see. Yeah, so essentially like we're looking like for different outcomes in that case, I believe. I guess if you can if you just draw like the I believe, yeah, for if we think about like the sum of the dice is at least 10, and if the dice are just are identical, let me think. Yeah, then the probability should be less. Yeah, and there should be a fewer total outcomes, because we do not count like as like 4, 6, and 6, 4 as the same.
So, and that also confused me, because now, like, the total number of outcomes you're changing, which, so sure, you're eliminating 4, 6, and 6, 4, but now the combination of 4 and 6 together is more likely than the combination of 4 and 4 together. So they're not equally weighted in the denominator. So each case isn't equally likely to happen. Whereas in this case, each case is equally likely to happen because it is one of the many possible cases.
Well, so it is like I guess it is like equally weighted. The way you're thinking about it is just like they're the same dice, so it's kind of like eliminate like those probabilities, I guess. So if you think about let's see. if you want to count like the probability of rolling like exactly like a 4-6 in as the 2 dice, then there won't actually be so the total outcome should not be 36.
Right.
And then you will also count like 6, 4, 6, and 6, 4 as different, as the same outcome.
So I get that they would be the same outcome, but sort of when you analyze that and sort of think about that, like in my brain, it doesn't really work, right? Because, so let's look at the two cases of, let's say 3-3 and 4-6. Whereas if we were analyzed them as separate dice, and then say that the combination, like you're going to get two different probabilities. That didn't make much sense. But there's two ways to roll a 4 and a 6. There's only one way to roll a 4 and a 4.
I guess it's because that if you're thinking about they're equally weighted is when you have only a single die. So if you're rolling like a 2 and then rolling a 3, it's the same probability as 1 or 6.
Right.
Yeah, but since we're counting for 2 identical dice, then the probability of rolling like a 4-4 and a 2-3 or 3 and 2.
Well, we can do that math right now, right? To get a 4-4, it's 1/6 times 1/6 because they're independent events. But to get the combination 2-3, we have 1/6 times 1/6 plus 1/6 times 1/6, right?
I'm saying that you cannot actually use 1/6 times 1/6 because this will give you 1/36. But right now we're saying that the total outcome should not be 36, which should be less if we're talking about 2 identical dice.
But the total number, so that's sort of my confusion, is that if the dice are identical, why are there less equally likely outcomes? Like if we count all of the outcomes, why is this outcome, which if calculated independently is more likely, why is it considered to be the same likelihood as the other one? Do you know what I mean? Like, why is the likelihood of the one outcome 2-3, which is identical, or in this context, identical to 3-2, have the same probability as 4-4?
I think you can get a coherent probability model out of this, but I think you might be confused because it's not going to work in real life, because no matter what, you have 2 distinct die by virtue of having 2 die.
It's a matter of the order making a difference. It's like a bag problem versus like a permutation problem.
In general, the order doesn't matter here.
But I mean, for the 2 distinct die, like 2-3 is different from 3-2.
They are matters. So it's like kind of like which one is 4 and which one is 6. If the red is 4 and then the green is 6, it's different than the red is 6 and the green is 4. That's when we count like the order does matter here. But I think if you're taking 2 identical dice, then the order doesn't matter because you're still gonna have the same outcome. But right here for 2 distinct dice, they doesn't count as the 2. They doesn't count as the same outcome.
Okay. So does that mean that 2 identical dice are not independent events?
Yeah, I think you can think that as that way. Yeah. So that's why you cannot actually use 1/6 times 1/6. If that makes any sense at all.
That makes a little bit more sense, yeah.
Okay. I think we will talk more about like the independency and also like conditional probability, like in next week's lecture video. So again, like if you have like any like further doubts on like all the definitions and how would you define like each part, you can also like ask MPS or just come to office hour. Yeah. So let's just move on for the discussion right now. All right, so the next question is another probability question. So I'm just gonna write it down. All right, so we suppose Jessica rolls an 8-sided die, and John rolls a 6-sided die. So we're asking about what is the probability that John's roll is higher than Jessica's. All right, I will give you guys some time to work on this one. I believe this question should be easier if you just directly count like how many are there. And then just use the definition of the probability. All right, let's talk about this one. So, what would be your sample space, like the total number of outcomes in this problem?
I think it'd be 6 times 8.
So I guess for this question, you can think about as they are distinct, since they are rolled by different people, and like one of them is an 8-sided die and the other one is 6-sided die. So you can just use the total number of outcomes would just be 6 times 8. So now we have a total of 48 possibilities. And then let's just denote E be the event that John's row is higher than Jessica's. Then what's going to be our N of E?
We got 5 plus 4 plus 3 plus 2 plus 1.
Yep. Do you just kind of want to explain how you get this?
So I just took it by cases. I didn't use any formula or anything like that. So if Jessica rolls a 1, then John can roll a 2, 3, 4, 5, or 6. And then just using that logic for each of Jessica's rolls. 5 is the last one where John can actually beat Jessica.
Yep. So the 5 right here actually means John has 5 choices to roll, and when Jessica rolls a 1, and then right here just means when Jessica rolls a 2, John can actually have 4 possibilities, and then for 3 and plus 2 and plus 1. And this will give you a total of 15. So now we should have the probability as N of E over N of S, which is 15 over 48. And if you simplify that, that's 5 over 16. Any questions on this one? Okay, the next one. So the next question, I'm also gonna write on this paper. I believe this question is a similar question you will have on homework 6. Let me see. All right, so let's do this one. So what is the probability that in 10 tosses of a fair coin, the result of heads appears at least 8 times? All right, 2 or 3 minutes to work on this problem. All right, so let's talk about this question. Okay, so in the chat says, does order matter for the number of possible outcomes? Okay, so for this one, we're actually counting for the result of the number of heads or the number of tails. So it actually does not matter if you first, so if your first die, like if your first toast has a tail and the second one has a head, or is the same as the first has a head and the second has a tail. So the order doesn't matter. But you cannot have repeat. Okay, so let's use the definition of the probability. So we first want to let S be the sample space, and let's first find out what is N of S. So like, what is the total number of outcomes?
Would it be 2 to the 10?
And how would you, like, which terminology to describe this formula?
For each coin flip, there are 2 possible outcomes, and because they're distinct and disjoint, and we're doing it 10 times, I multiplied them together.
Yep. So I'm actually looking for the word that is an order list. So where 2 is like your N and 10 is your R. So you have 2 choices and you want to toast it, and you have 10 toasts. All right, and that should give you 10, 24. That's your N of S. And let's look at N of E. How would you determine this part? So in the question it says appears at least 8 times. So we want the event have at least 8 has appeared. How would you count for that part?
I did 0, 1, or 2 tails.
Yep. So that's one of the ways. And in fact, that should be the easiest way, I believe, as far as I can think of. So at least 8 has is equivalent saying that at most 2 tails. Yeah, it's the same thing if you're in the chat, if you're using like 10 choose 8 and plus 10 choose 9 plus 10 choose 10. That's the same as the at most 2 tails. So you should get the same answer.
For 10 or 2 to the 10, that takes order into account, right?
Let me think. Yes, it does. I guess if we're thinking the way as for each toast you have 2 different choices, and it should give you the different outcomes. So this is an identical toast, because for each toast they're independent. They are identical, but they're independent. I guess for the previous question, when we talk about like 2 identical dice, why they're not independent, because like the 3, 4 and the 4, 3 are actually influencing each other. You cannot actually count this part as 2 different outcomes. But in this one, why we're saying that they are they're identical but still doesn't affect the probability is because for each of the toes, whatever, like it doesn't matter like which one you get, you were just done with this with this term. And for the second one, you would just start from the beginning, and no matter what the first one you chose, it doesn't affect the result of the second one. Is that more clear or? Okay. Okay, so just back to the question. Let me just finish this one. This one should give you 45 plus 10 plus 1 and over 1024. And that's 56 over 1024, and that's 7 over 128. Okay, any other question? I think what he means by identical is that we're using the same fair coin each time. All right, so we still have some, let's see, we still have 6 or 7 minutes left. Are there any homework questions you guys want me to talk about? It can be either on homework 5 or on the new homework 6.
I was curious for the first example, if we were trying to count the number of possible outcomes for those identical dice, what is the formula for that? I mean, I just like counted them up, but is there an easy way to calculate that?
I think for dice, you can just count them up since there's since the numbers, well, I guess the calculation's not going to be too bad. Let me think if there's a easier way. There should be. Let me see. I guess the way I'm doing it, I would just probably, because 1, 1, and 2, 2. Well, let's see if we can just have this table right here. So if they are distinct, then we will just count we'll just count each of the boxes where we'll give you 36 total outcomes. And for the identical dice, it will instead be a combination instead of a permutation. Yes, it should be, we should use combination instead of permutation, since the order doesn't matter in this case. And then here the coin is identical because it's an odd order list instead of an order list.
So is it just 6 choose 2 would be the formula?
Six choose 2. Let me see. And you're talking about like the total outcomes?
Yeah, the total outcomes for the 2 identical dice.
So I think 6 choose 2 should give you 15. And you should also, so 6 choose 2 basically means you can just choose, you cannot have repetition. So instead of, in addition from 6 choose 2, you probably want also plus 6 to account for the possibilities that's for 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. So I guess what you need is that 6 choose 2 plus 6. Is that right? Let me think. Yeah, I think that should be the total number of outcomes if we're so for the C 6 plus 2 minus 1 2. Yeah, that's like the formula for the order list. Let me just calculate this one and see what we got here. So that's 7 choose 2. Okay, so this one actually equals to 6 choose 2 plus 6, which should all give you 21. I just put that in the calculator.
Oh, thanks.
Yep. So for, I guess for the, if we're counting for the identical 2 dice, and then the total outcomes would just be an on-order list, since we can have repetition and order doesn't matter. Yep. And for this part is actually we're using like the set where we didn't count like the repetition part, and that's why it's just plus 6. So currently we only have like 6 pairs that can't have repetition. Yeah. So we should have total 21. All right, so just go back to the question. I think I haven't answered that. So here the coin is identical because it's an order list instead of an order list, right? So I think the coin, we consider the coin as identical only because we're using the same coin for each toast. And then because it's an order list instead of an order list.
It's okay if you don't need to answer it. My brain is kind of tired of thinking right now. So
Okay. Yeah, I guess the way you're thinking about it is if you wanted to choose like for the event part, that's where we want to use the set, where it's actually a set problem where you cannot have repetition and order doesn't matter. But in terms of the total number of outcomes, I think it's an order list.
I was more talking about like when, so like for the total number of outcomes, yeah, that one, the order matters, but for the other part where like order doesn't matter, where it's just asking if it contains at least 8 heads, that part would be an unordered list.
So for an unordered list, is that we can have repetition. So I guess what the repetition actually means here is that for one single toes, you cannot have 2 heads. You can either have 1 head or 1 tail.
Oh, I see. So it would be a set then?
Yeah, that's
Okay.
why we cannot have repetition. So the repetition here doesn't actually referring to like they have like the same, we have like the same fair coin each time.
All right, that answers my question. Thanks.
All right, so we're over time. So that's what we're gonna have for today. So you're free to go.